Hi, everyone, and welcome to the voiceover lecture for our independent t-test practice problems in Psych 3530. So what I'm going to be doing in this lecture is going step by step over our two practice problems that were at the end of the um, independent t-test math and theory lecture that is posted on iCollege. In addition to the voiceover here, I'll also obviously be posting the static PowerPoints for this lecture on iCollege in case you just need to, recheck your math or look at something and you don't need to watch the whole voiceover video. So the sort of strategy we're going to take here is I'm really going to spend some time with problem number one, breaking everything down and sort of re-explaining everything. And then we'll go a little more quickly through problem number two. I won't speed through it, but maybe I'll just kind of gloss over some of the things that are equal or similar to problem number one and highlight the things that are different from problem number one to problem number two. So let's get started. So here's our first problem. Health psychologists want to know if men have higher resting heart rates than women. They collect data from 10 men and 10 women. We can see the data provided here. We have our 10 men and their resting heart rates. This is usually beats per minute, and women and their resting heart rates in beats per minute. If alpha equals 0.01, what should we conclude? So our research question is about gender and resting heart rates. Our independent variable is gender. Our levels are men versus women. Our dependent variable, our outcome, our measurement, is resting heart rate. Here are the main steps that we need to take, sort of broken down piece by piece and bit by bit. And so we're going to walk through each of these in turn until we end with our APA-style conclusion. So first, what we need to do is define our populations and our null and research hypothesis. So obviously population 1 is men, population 2 is women, easy peasy. With hypotheses, I like to begin with defining the research hypothesis because it's the most obvious one, because it's just the research question, right? So our research question is, do men have higher resting heart rates than women? So our alternative or our research hypothesis is that population 1, men, will have greater resting heart rate than population 2, women. Now, defining the null hypothesis is simple, but maybe a little bit more confusing because the null hypothesis is basically everything else, right? So if the alternative is that men are greater than women, then the null is that men are less than or equal to women. Basically, the null is every possible eventuality that would make the research hypothesis incorrect. So if we think men are going to be greater than women, then we're incorrect if men are less than women. And we're also incorrect if men are equal to women. So that's the null, the nothing, right? Our research hypothesis didn't happen. It didn't come through. So that's the null hypothesis. Notice that these inequalities are mutually exclusive, meaning that only one of them can possibly be true at any given time. They can never both be supported. We will end up supporting one of them or the other. And remember that we begin by supporting the null, and we only move to the research hypothesis if our data suggest that we should. Step 2 is probably the longest, most mathematically involved step. We need to take the data from both of our samples, so our sample of men, and then over here, our sample of women, and we need to complete a sum of squares table so that we can calculate a variance and a standard deviation. So we take all 10 men and we find their mean, it's 65.2. And we take all 10 women and we find their mean, it's 61.9. The next step is to take each individual score, we call these X, right? X's, each individual X, and subtract the mean of that sample to find a difference score for both our males and our females. So we do that, and it looks like this. 68 minus 65.2 is 2.80. Always remember that we want to round to 2 decimal points. 2 decimal points. 57 minus 65.2 is negative 8.20. And, so on and so forth. The same calculations for the women. Every individual minus the mean of that sample. Make sure that you do not get your sample means mixed up. That would be terrible, because then your sum of squares tables would be wrong from the beginning, and everything else you do will be wrong for the rest of the problem. So be very careful at this step. Pay great attention to detail. Make sure that you are using the correct numbers and doing all of the correct calculations and rounding correctly. Once we have our difference scores, we take each difference score and we square it. That's x minus m to the second, right? So the difference score squared, 2.8 times 2.8 is 7.84. 22.8 times 22.8 is 519.84. We do the same thing over here for the women, right? 2.1 times 2.1 is 4.41. 6.1 times 6.1 is 37.21, so on and so forth. So we have our squared deviations, and then we sum them, right? We sum the squared deviations. That's where we get this name, sum of squares. We sum the squared deviations to give us this measurement of variability within each sample. So we can actually see, we can tell already that men's heart rates vary more than women's heart rates do, right? See, they have a greater amount of variability. Their sum of squares is higher. The next step is to calculate what we really need, because sum of squares is good, but arithmetically, it's not exactly what we want from a measurement of variability. So what we really need to do is turn the sum of squares into a variance. So we have 10 participants. The samples happen to be equal, 10 men and 10 women. Thus, each sample has 9 degrees of freedom. We have established our sums of squares. And so we calculate a variance by taking this sum of squares and dividing by degrees of freedom. So 1723.60 divided by 9 for our men gives me a variance of 191.51. And 608.9 divided by 9 for our women gives us a variance of 67.66. So once you have the variance, that's actually all you need for calculating your t-test. Right? We could move forward from here and be fine with getting our calculated t. But because we're here, we might as well go ahead and calculate a standard deviation for each sample, because that's what we need to report in the APA style conclusion. We need to report the descriptive statistic standard deviation for each sample. Standard deviation is just the square root of a variance, and we get 8.23 for women and 13.84 for men. So we can see, because men have a higher standard deviation, men's heart rates vary against each other more than women's heart rates vary against each other, meaning women are on average more similar to other women in their heart rates. Men are on average more different than women in their resting heart rates. Okay, so what we really want to focus on at this point is carrying over 2 values from each of these tables. The means, because that's going to be involved in our numerator. 3 values from each table. The means, that's going to be our numerator. The variances, that's going to go into our denominator. And our sample size, our n, that's going to go into each denominator as well. So let's do the easy part, the numerator. Here's our t-test formula. Mean difference on the top. Easy peasy. The mean for men minus the mean for women. and we have a difference of 3.3 beats per minute between the average male and the average female. So this tells us that our groups do differ, right? By 3.3 beats per minute. Men have a nominally higher resting heart rate than women by a factor of 3.3 beats per minute. That's what our numerator tells us. What our denominator tells us is whether or not 3.3 beats per minute is a substantial amount of variability. Because the denominator is going to tell us, well, how much variability should we expect on average just from random sampling? Because if I collect data from 10 men, and then I collect data from 10 other men, and then I collect data from 10 other men, they're going to vary in their heart rates. The same thing for women. So we can expect some amount of naturally occurring variability in the population. We have observed a difference between men and women of 3.3. The question is, should we care about that difference? Is this difference a substantial or a significant difference? That's what our denominator is going to tell us, because it's going to tell us how much difference we should, on average, expect. And if we are going to claim that men and women differ in their heart rates, then we would want this number, 3.3, to be much larger than the average amount of variability we can expect that occurs in the normal population. We want the difference to be above and beyond the expected difference. So now we need to calculate our denominator. We pull in the numbers we need. S squared is the symbol for variance. So we can see we have S squared 1, S squared 2. That's men and women. So we pull in those variances divided by their sample sizes of 10. We do the math. We end up with 19.15 and 6.77. We follow order of operations and we add those two together. 19.15 plus 6.77 gives me 25.92. That's the result of everything under the square root signal or symbol. I guess not signal, the square root symbol. So we take the square root of 25.92 and our denominator ends up being 5.09. So our numerator was 3.3. Our denominator was 5.09. What this 5.09 means is that that's kind of roughly the amount of variability we should expect to exist randomly and naturally between men and women. So if we should expect about a difference of 5 beats per minute, the fact that we found a difference of 3.3 doesn't look very special now, does it? That's what our t-test is going to tell us, because we take that numerator and we find the ratio of our observed difference divided by the expected difference, or the amount of, you can think about this as error, the amount of error that we would expect in normal population sampling. And so we produce a very small t-value, 0.65, because we found a difference of 3.3. But what the t-test is telling us is that, we should expect a difference of 5. So 3.3 doesn't look very special if we should, on average, expect a difference of 5. So we produce a small t-value, 0.65, and this is going to end up being not significant. We're going to end up, spoiler alert, we're going to end up concluding that men and women do not differ in resting heart rate, because the difference we observed is not substantial when you compare it to the difference that we should expect to occur on average naturally. So now that we have our observed t-value, we need our critical t-value, our line in the sand, our benchmark. We need 3 pieces of information for this. Total degrees of freedom, which is degrees of freedom of men plus degrees of freedom of women. 9 plus 9 is 18. Alpha was given in the problem as 0.01. And we have a one-tailed test because we made a specific directional hypothesis. Men will have higher resting heart rates than women. So because of our degrees of freedom of 18, we know we're working on this row, this 18 row, right? Degrees of freedom. We come down, we find it, 18. We know that we're working off of this row because we have a one-tailed test. And we find our alpha of 0.01. And that tells us which column to use. And so we just merge the row of 18 degrees of freedom with our alpha column to find a critical t-value of 2.552. So now we need to compare our observed t-value with our critical t-value. We observed a t of 0.65. We are only going to be convinced if our t-value was beyond 2.552. That's our line in the sand. That's our benchmark. Notice that we aren't anywhere even close to it, right? We observed something that's over here in the main fat part of the curve, right? This tall area of the curve. What that means is that what we observed is very typical. It is exactly what we should have expected to happen. And we are not convinced by typical occurrences. We are convinced by extreme occurrences. And so because we were not more extreme, meaning beyond the benchmark, because we were not more extreme than the benchmark, then what we do is we stick with the null, right? And this is the confusing language that we use in science. It's a kind of a double negative. We fail to reject the null hypothesis. And remember, the null hypothesis is the idea that the research hypothesis is incorrect. We said that we wonder if men have higher resting heart rates than women. We start with the idea that they don't, that they're either less than or equal to. And we will only move away from this default location if the data suggest that we should. The data do not suggest that we should. The data are not convincing. So we retain the null hypothesis. We fail to reject it. So imagine at the beginning of the experiment, you set up your null and your research hypothesis, and the first thing you do is you grab the null hypothesis and you hold it tight because you're going to keep it. You're going to stay with the null unless the data make you reject it. The data do not make us reject it because the data are not extreme enough. They are not convincing enough. And so we retain or fail to reject the null. So what we have is a not significant difference. We are going to conclude that men and women, are equal, or that men do not have higher resting heart rates than women do. We do not need an effect size. We don't need Cohen's d because we're not significant. So we can just breeze on past that one and get right to our APA style conclusion. Just three major parts. First, we introduce our test and our research question. An independent t-test was conducted to assess whether men have higher resting heart rates than women. Part two, we provide our descriptive and inferential statistical statements, along with sort of the result, right? What happened? The resting heart rate of men with a mean of 65.2, and here's where our standard deviation comes back from that sum of squares table, 13.84, is not significantly higher than the resting heart rate of women with their descriptive stats. T, degrees of freedom, equals t-value, were not significant. Thus, men do not have higher resting heart rates than women. That's our take-home message. Explain it to a fourth grader. The goal with this last sentence is that someone who has no idea about anything else you said in the first statements, they have no concept of experimental design, they have no concept of statistics, that person could understand your last sentence and could walk away with the take-home message. That's the goal here. Okay. We're going to move on to our second problem. I'm going to go a little bit more quickly because I don't need to repeat myself about necessarily all of that, but I'll just point out the things that are different here. Off the bat, something we can notice that's different is that we don't have an equal number of participants in each of our groups. That's fine. It's perfectly okay. The formula for a t-test can handle that. Now, ideally, when you conduct research, you have equal numbers of people in each group, but that doesn't always happen. Research is messy. People are messy. People drop out. You run out of time. There are a whole lots of contingencies built upon research that might make one group of people have more or have a greater or less number of people than the other group. So, for example, in this experiment, we're asking the question about the impact of drug use on cognition, specifically if long-term ecstasy use leads to lower memory scores. So we're going to have a one-tailed test, lower, that's directional. So we test the memory of 10 non-users and 8 ecstasy users, drug users. Now, it's possible that, because they are ecstasy users, that's maybe a rare population. It's a small population. Maybe they're difficult to find. It's difficult to get them to admit that they use ecstasy and then come in for testing. Lots of maybe we could call research on sensitive issues has this problem. And so because of that, we couldn't get to 10 drug users. We were only able to sample 8 of them versus sampling 10 non-users. If alpha is 0.01, what should we conclude? You can see the data below. And we're going to walk through those same steps that we did with problem number 1. We define our populations, drug users, non-drug users, and then we define our hypotheses. Again, start with the research hypothesis because that's the most obvious one because it's just the research question. Does long-term ecstasy use lead to lower memory scores? So, is our population of drug users going to have a lower, less than memory score than non-drug users? The null is just everything else, would be that they are greater than or equal to, Make the inequalities mutually exclusive. We do the same thing. I'm going to breeze through this again. Sorry about that. It's a little funky over here. Breeze through this again. Just press pause if you need to check your math, but all the logic is exactly the same. The things to point out are that we only end up having 8 individuals and thus 7 degrees of freedom in the drug user group, whereas we have 10 individuals and thus 9 degrees of freedom in the non-drug user group. Everything else is the same. You do all the math the same. Press pause if you need to check your math, and then click play when you're ready to pick back up. Okay, so we're going to move on. We're going to pull our 3 values from each sample that we need: the mean, our N, and our variance. So we use the mean in the numerator of our t-test. Drug users scored 6.13 on average. Non-drug users scored 8. So drug users are 1.87, memory points lower than non-drug users. So again, we have a mean difference. It looks like nominally drug users have worse memories than non-drug users, but we need to calculate this denominator to see if it's a significant difference. We plug and chug with our variances of each sample divided by each sample N, add them together, take the square root. We end up with a denominator of 0.60. Then we take our mean difference of negative 1.87. Remember to carry this negative sign over. It's important. Divided by our denominator of 0.60 gives us a t-value of negative 3.12. Again, carry over the negative because it means that they're lower, right? It's telling us the directionality of the effect, considering we made a unidirectional prediction, right? We made a one-tailed hypothesis. So whether our t-value is in the negative or the positive side of the curve is really freaking important. We need that negative sign because it tells us they're on the left side of the curve, not the right side of the curve. Next, we need our critical t-value. Everything is the same. Alpha is 0.01. We still have a one-tailed test, except that we have 16 degrees of freedom because we had 7 degrees of freedom from our drug users and 9 degrees of freedom from our non-drug users. The table returns a value of 2.583. We need to take that value and understand that because we made a negative one-tailed test, we need to make, or one-tailed hypothesis, we need to take 2.583 and make it negative so that it's on the appropriate side of the curve given the directional hypothesis we made. Had we made a positive directional hypothesis, then we would just keep positive 2.583. The table doesn't have negative values because the curve is equal on the left and the right side of the mean, right? The curve is equivalent, it's symmetrical. So having a negative table would just be unnecessarily redundant. So we only have a positive table. You, as the researcher, just have to know and remember that it returns a positive value, but we made a negative prediction. So we need to put that negative in front of it. Now let's compare our observation to our critical value. We observed a t of, here again, the negative is important, negative 3.12, so that we're on the appropriate side of the curve. We compare that to our critical t of negative 2.583. We are beyond it. We are more extreme. Drug users are a lot different from non-drug users. That's what this means. It means we have an extreme result, right? Look how improbable this result is, right? As the curve goes down, then the probability gets lower. So this is a very improbable result. It's beyond our cutoff, so it convinces us. It's good evidence that drug users have, in fact, worse memories than non-drug users. So remember, we were holding on to the null, but in this case, because we're convinced, we reject that null. We push it away, we let go of it, and we throw our support behind the research hypothesis, which was that drug users have lower memory or worse memory than non-drug users. Because we were significant, we need to calculate a Cohen's d effect size. Numerator is the same as our t-test numerator. Sorry, this is 2 minus 1, 1 minus 2. Just be consistent with whatever you did in the t-test. Doesn't technically matter, but just be consistent with which mean you put first and which mean you put second. So that's the same, negative 1.87 as our t-test. Our denominator, again, just plug and chug some basic algebra here. SD stands for standard deviation. SD squared is just the variance. So we take our variances that we used earlier, we plug them into this formula, meaning we add our variances together, and then we divide by 2. Basically, we're finding the average of the variances. Then we take the square root of that value, and so our denominator is 1.59. Negative 1.87 divided by 1.59 gives us negative 1.18. And I know I said that the negatives matter, but for Cohen's d, they don't. Sorry, it's confusing, it's inconsistent, but that's the way it is. For Cohen's d, whether it's positive or negative doesn't matter. Let me explain why. We always just go with the absolute value. So Cohen's d should always be positive because Cohen's d is a measurement of the magnitude of the effect, the size of the effect. Your t-value is a measurement of the directionality of the effect. So we already know the direction. So all that Cohen's d cares about is the magnitude, the size of the effect. So if Cohen's d turns out to be negative, you just drop the negative and you go with the absolute value. And lastly, of course, our APA-style conclusion. An independent t-test was conducted to assess whether drug users have worse memory scores than non-drug users. That's our research question and our statistical test. Next up is our descriptive and inferential statistics. The memory scores of drug users. Mean is 6.13, standard deviation is significantly lower than the memory scores of non-drug users. Mean equals 8, standard deviation. That's our descriptive statistics and our explanation of what happened. Then we provide our inferential statistics. T tells them we did a t-test. Degrees of freedom equals 16. That's 7 from the drug users, 9 from the non-drug users. Equals our t-value negative, keep that negative here, 3.12, comma, p is less than 0.01, meaning, so this is alpha. P stands for probability. So what this tells us is that the probability of this t-value is less than 1%. It's convincing. It's rare, so it convinces us. That's really what alpha means. So the probability of this result was less than alpha, less than 1%. Our Cohen's d was 1.18, which if you remember back to our discussion of magnitude of effect sizes, this is a large effect. So this is robust, we might say. It's important. It's real. It hits hard, right? That it's not just a small nominal difference. This is a big deal. That's what that D of 1.18 tells us. And lastly, our take-home message. Thus, drug use lowers memory abilities. Okay, that's it for these practice problems. Thanks for listening. Again, feel free to watch this as many times as you need. Press pause whenever you need to. You can always look up the static PowerPoints on iCollege if you don't want to hear me ramble on about it anymore. So thanks, everybody, and I will talk to you later.